good job explaining the other bases. So before we get started with the notes, I'm going to go ahead and introduce you to base 10 blocks. So base 10 blocks look something like this. These are like plastic ones. There are foam ones. There are lots of different kinds. They come in different colors, obviously. And then we also have this piece right here. So this is like a 3D cube. So what this is this represents a unit. And then if I put 10 of these together, so 3, if you were in class right now, you would each have your own set, and we would be playing with them. But if I put 10 of them together, it makes this long piece, which we call this one piece that we call a unit. This we call a long, and one long is equal to 10 units. And then 10 units, let me get all the pieces, 1, 2, 3, 4, 6, 7, 8. Get out 2 more. 9, 10 longs is the same thing as what we call a flat. Okay, and then I'm not going to do this, but 10 flats is equivalent to 1 cube. So essentially, 1 unit right here, this long is equal to 10 units. This flat is, there's 10 units on this, 10 on this, so 10 times 10 is 100. And then if this is 100, 10 of those would make 1,000 here. So these are manipulatives that you can use to represent place value. So this would represent the ones place, the units would. This would represent the tens place. This would represent the hundreds place. This would represent the thousands place. So for example, the number 13. If I had 13 units, I could put 13 units out like this, and that's no problem. Like, it's not a big deal. But if I needed to put 130 units, I wouldn't want to have to count out 130 of these, much less I probably wouldn't have 130 of those. So it is beneficial to be able to use other pieces. So with 13, I could trade out 10. So let's see, it's 2, 4, 6, 8, 10. I could trade out 10 of these for a long, because 1 long equals 10 units, right? So I could trade out 10 units for 1 long, and now I have the number 13. And if you'll notice, the number 13 is 1, 2, 3 ones and 1 10. So 1 10, 3 ones. If I wanted to do the number 257, the way I would demonstrate 257, I don't want to count out 257 of my units, so instead I could use my flats, because 2 flats represents, 1 flat represents 100, so 2 flats would be 200. So if the number was 257, I don't want to count out 57 of these units now, so I'm going to use some tens. I have 1 10, 2, 3, 4, 5, and then 7 units. 1, 2, 3, 4, 5, 6, 7 units. So that's how you would represent the number 257 with base 10 blocks. Okay, so we're going to pause from those for a minute, and let's talk about our base 10 system. Okay, so our number system, base 10. Okay, so first of all, let's talk about the digits that we use in our number system. The digits that we use are the digits 0, so these are our digits for our number system, 1, 2, 3, 4, 5, 6, 7, 8, and 9. You can make any number using any combination of these digits, or using a combination of these digits. Okay, so the number 10 is not a digit in our system. That is using the number 0 and the number 1 to represent 10 things. The number 52 is not a digit. The number 52 uses the digit 5 and the digit 2 to represent a number of 5 tens and 2 ones. So place value is what our system is based on. Okay, so notice our system has a 0. Other number systems don't have a 0 in it, like the Egyptian and the Roman numeral number system didn't have a 0. Base 10 does, and that's huge. It lets us be able to do place value when other systems didn't. So the big things about our number system is it has a 0, and we can use place value, whereas other systems couldn't use place value. So let's talk about different ways we can represent numbers with our number system, and represent it using our base 10 blocks, and then we can move into other bases. So there are 4 representations for a number in our number system. So I'm going to split this into 4 groups, or 4 sections. Okay, so let's talk about the number 1,478. Okay, so the number 1,478, we can represent it in a standard method, and that is 1, 4, 7, 8. And we usually put a comma after the 1 just so that it's easy to read it quicker. Okay, so this means I have 1,478 units. This is not a digit. This is a combination of the digit 1, 4, 7, and 8. I took those from up here and I made a number out using those digits. So place value. How many 1s do I have in this digit? How many units of these do I have? I have 8. How many 10s do I have? I have 7 10s. How many hundreds do I have? I have 4 hundreds. And how many thousands do I have? I have 1,000. Okay, so the digits represent how many of that place value that you have. Okay, so we can represent this number using words. So in words, you would read this 1,478. You would not use the word and in here. So let's write it out with words. 1,478. Okay. We can also write this using expanded form. And expanded form is a way of showing the number using the place value. So within expanded form, I have 2 ways I can do it. I can do one without exponents and one with exponents. So the first way we're going to do is without exponents, and then I'll show you with exponents. So without exponents, to do expanded form, you tell what digit you have in what place value. So I have 1,000. So 1 times 1,000. I have 4 hundreds here. So 4 hundreds. I have 7 tens. So 7 tens. And I have 8 ones, or 8 units. Okay, so that's expanded form. It's telling how many of each place value that you have. I can do the same thing with exponents. With exponents, instead of writing it as 1 times 1,000, I write 1,000 as a power of 10. So 1,000 I could write as 10 to the 3rd power. 100 I could write as 10 squared. So 4 times 10 squared. 10 I would write as 7 times 10 to the 1st power. And 1, the way you won't write 1 as a power of 10, is 8 times 10 to the 0 power. This will come into play later on next week when we're talking about changing bases a lot more, and towards the end of this lesson. Okay, so just notice 1, 10, 100, 1,000, they're all powers of 10, and this is a base 10 system. Okay, so now here let's show with base 10 blocks. So if I was going to actually use my base 10 blocks here to represent the number, it would be 1,000, 4 hundreds. Let's see if I can get it all on the screen for you. 1, 2, let's do it like this. 3, 4 hundreds, 7 tens. So 1, 2, 3, 4, 5, 6, 7, and 8 ones, or 8 units. 1, 2, 3, 4, 5, 6, 7, 8. So that's how you could represent using using base 10 blocks the number 1,478. So let's put this on our paper and show how we write it on our paper. Later on this semester, we'll do a project where you make all the manipulatives out of foam, or you can buy them, and we'll talk about that more later. So you will have your own set of base 10 blocks by the end of the semester. So, drawing base 10 blocks here, I need to draw 1,000, and that's a cube, so you draw a cube on your paper. I'm going to label them just so that you can remember what they're called. I need 4 100s. Those are 4 flats. We just use a square to represent flats. I need 7 10s, and we use longs to represent 10s, so it's just a stick, basically, or the number 1. These are called longs. And then 8 units. You could draw a little square. No, you don't want to draw squares because the squares look here. So you could draw circles. You can do dots, but it's just easier to see the circles if you do it like that. And these are called units. So when you are doing this with your students, when you're introducing base 10 blocks, especially the younger grades, sometimes it's helpful to do it with a base 10 mat. So here's an example of a base 10 mat, and you can just get these off the internet. I got this, I think I just Googled it and printed it. But this gives you a place to put all your units and put the 10s that you have, and you need a bigger mat if you're doing hundreds and thousands. But it shows how they each have their own spot and the order that they need to go in. So a base 10 mat might be good for your classroom. Maybe, like, depending on what grade level you're teaching. If it's like kindergarten or first grade, you're not getting into 4-digit numbers. You're getting in just 1, 2, maybe into 3-digit numbers at the end of kindergarten. So you can spread this out, or you could do it on a big sheet of paper, you can laminate it, so on and so forth. So this might be a good resource for your classroom. Okay, so there's 4 representations for your base 10 number, and this is some stuff that you're doing on your homework, is write in expanded form, write in words, so on and so forth. So, the first problem we're going to talk about, we've already done this, expanding this in base 10, but we're about to start expanding things in other bases. So I'm going to go ahead and show you how we would expand something in base 10 the same way we would do in other bases. So expand the number 4,678. So the first thing you have to think about, this is in base 10. The first thing you have to think about is what each of those numbers represent. So I have these 4 numbers, and these each represent a power of 10. So going from right to left, it's 10 to the 0 power, 10 to the first power, 10 squared, 10 to the third power. Because this last number on the end on the right is always your units, and it's always going to be something to the 0 power. Okay, so then in this case, this is the tens place, this is the hundreds place, this is what we call it, and we know that this is, and this is the thousands place. And it's called that place because 10 squared is 100, 10 to the third is 1,000, 10 to the first is 10. Okay, so if I expanded this, it would be 4 times 10 to the third, plus 6 times 10 squared, plus 7 times 10 to the first, plus 8 times 10 to the 0. I can work that out a little bit more. 4 times 10 to the third is 4,000. 6 times 10 squared is 600. 7 times 10 is 70. 8 times 10 is 8, which is the number 4,678. But you say, that's silly. I already knew that. Right. We can see that because we're in base 10. But if we switch over to other bases and do this in other bases, you can have any base you want to. The Babylonians used base 60 system, and your reflection reading tells you a little bit more about that, and so I kind of want you to reflect on that. The first one, I have manipulatives for this one, so that's what we're going to do. We're going to do base 5 first. Okay, so here's an example of a base 5 manipulative. So that's the flat. Here's the long. These are just foam, that's why you can't see the actual grid on them. But I know it's base 5 because if I lined up 5 units, these are real little, so give me a second. If I line up 5 units, I get the length of a long. Instead of 10, it's 5 now. If I line up 5 longs, sorry, I should have had these pulled out already. 5 longs, I get the shape or the length of a flat, right? and then I don't have a cube, but 5 flats would make a cube, so on and so forth. So base 5 is different than base 10 because our unit still represents 1. Our long, instead of representing 10, now represents 5. Our flat, instead of representing 10, think how much the flat represents. 5 on this one, 5 on this one, 5, 5, 5. 5 times 5 is 25. Okay, so maybe let's write that down and we'll do a problem with base 5. So for base 5, our unit is still just a unit. I spelled that wrong. It's still just a unit. It still equals 1. Our long now is 5. Our flat is 5 times 5, which was 25 units. And I didn't have one, but if I did, our cube would be, if you think about it, 5 flats. So it would be 5 times 25, which is 125 units. And notice, this is 1 is the same thing as 5 to the 0 power. 5 is the same thing as 5 to the first power. 25 is the same thing as 5 squared. And 125 is the same thing as 5 to the third power. Okay, so we have the same exponents. It's just the flat represents a different number than 100. The cube represents a different number than 1,000. Okay, so we're just going to do 2 problems today. Let's take a number in base 5 and put it in base 10. So basically, I'm going to give you some number that looks like this. Okay, I'm just making it up. Some number that looks like this, and I want you to tell me how many units are in that number. Okay, so let me turn the page. So our example, we'll ask you to expand the number 4132. And if you see the little parentheses with the 5 or written out 5, that says that this number is currently in base 5. This is not the number 4132. This is 4132 in base 5. And I want to put this into base 10. So I want to figure out how many units are in this, basically. Okay. So similar to how we did it before, kind of like the idea with the base 10 or base 5 blocks, I'm going to write this with my place value and think about what my place value is for this problem. Okay, so I have 4132. The 2 is the unit spot, right? So that's going to be 5 to the 0 power, which is 1. Okay, so this will always be, no matter what base you're in, this is always going to be 1 because it's always going to be your units. This 3 is your longs. So I have 3 longs. And in this case, it's 5 to the first power, which is 5 units. This spot right here is flats. So I have 5 squared, which is 25. So a flat represents 25 units. And then this is the cube spot. And I have 5 to the third power, which is 125 units. Okay, one thing real quick to let you know about is the choice of digits here in base 5. The only options I have for digits are 0, 1, 2, 3, 4. I can't use the digit 5 in base 5. I can't use the digit 6 in base 6. And the reason why is because if I had, let's say I had 6 longs. If I had 6 longs, if I was in base 5, I wouldn't put 6 longs down. I would group these together and turn them into a flat. And so 6 longs is actually 1 flat, 1 long. Does that make sense? I hope so. I can do another example if I need to. If I had units, let's count how many units this is. If I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. In base 5, I wouldn't leave it as 10 units. I would actually group 5 units together here to make a long, and another 5 units here together to make another long. So actually 10 units in base 5 is 2 longs. Okay, I hope that's helpful in understanding why my digits can only be 0 through 4. So if I want to figure out how many units total I have in this number that's in base 5 right now, I'm going to expand it the same way I expanded before. So it would be 5, I'm sorry, that's a 4. I have 4 of these cubes, so it's 4 times 5 to the third. 1 times 5 squared, I have 1 flat. 3 longs, 3 times 5 to the first power. And 2 units, 2 times 5 to the 0 power. So I can work this out. 4 times 5 to the third power is 125. 1 times 5 squared is 25. 3 times 5 to the first is 5. And 2 times 5 to the 0 is 1. 4 times 125 is 500. 1 times 25 is just 25. 3 times 5 is 15. 2 times 1 is 2. If I add this up, 500 plus 25 plus 15 plus 2, let's see, 25 and 15 makes 40, plus 2 is 42, so 542. So my answer is 542 in base 10. Make sure to either put the parentheses to show the base you're in, or to write what the base is so that we can understand what we're doing right now. Okay, let's do one more. In this one, we're going to do base 2. Okay, so base 2. So for example, if I had the number 1011 represented in base 2, and I want to put that into base 10, I want to figure out how many units that actually is. So the first thing we're going to think about is what digits can I use in base 2? So base 2, I don't have a manipulative for, but the idea is a unit would just still be 1 unit, right? 2 to the 0 power is just 1. A long, in this case, how many units make a long for base 2? 2 units make a long. So this would be 2 to the first power, which is 2 units. A flat would be 2 longs put together, which would be 2 squared. So 4 units make a flat. A cube would be 2 longs put together. I'm sorry, 2 flats put together, which would be 2 to the third power, which is 8 cubes, 8 units. I'm sorry, I said cubes, 8 units, like at the little cubes, that's what I meant. Okay, so the choice of digits here, I could have 1 down, but once I put 2 down, that's now my long. Okay, and then I could put down, this is not a very good example, but I could put down, once I put 2 longs down, that now becomes a flat. And I hope that makes sense. Okay, so this number right here, 1011, has 4 digits in the place value. The first one's in the units place, which is 2 to the 0 power. This one's in 2 to the first power, 2 squared, 2 to the third power. So to expand this number, I have 1 of these cubes, 1 times 2 to the third. I have 0 of the flats, 0 times 2 squared. I have 1 of the long, 1 times 2 to the first, and I have 1 of the units, so 1 times 2 to the 0. I can work that out now. 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. 1 times 8 is 8, 0 times 4 is 0, 1 times 2 is 2, 1 times 1 is 1, and 8 plus 2 plus 1 is the number 11 in base 10. Okay, so this idea of different bases is hard to understand. And the reason why it's hard to understand is we are so used to this system right here, the base 10 system. Your students are not used to a base 10 system, and you can tell that by like when they're counting, they'll put numbers like 11D12, or like put random numbers together, so they just don't understand the idea of place value, specifically kindergartners, first graders. So it's super important for them to understand this base 10 system. you will more than likely, unless you're in a higher grade level, not teach other bases to them. The reason why we're going over the other bases is so that you can understand the idea of the base system that's so natural to us. So this is frustrating probably. Some of this is confusing. And the idea is this is where your students are at when you're talking about a base 10 system and talking about place value. So you can kind of see where they're at and understand it better so that you can better explain it to your students at a different time.